Derivatives with natural logarithms, quotient rule, Lagrange's notation. So, as I've explained in previous videos, ln of x, when you have this function and you derive it, you end up with 1 over x. That's just how you do it. I will do a video in the future showing how they got to that, but when you derive ln of x, you get 1 over x. And this is just the quotient rule, the way this bloke does it. Just, you have a function fx over a function gx within hx. When you derive hx, this turns into this. The derivative of fx multiplied by gx minus fx multiplied by the derivative of gx all over gx squared. So, let's do some examples. Get right into it. So, example 1. Say we have a function hx, and we'll have inside ln of x over 3x. When we have a function over another function, we use the the quotient rule. Don't use the product rule. Well, you can, but I'll show that later as well. This is officially quotient. So, fx will make equal to ln of x, and gx will make equal to 3x. Only because fx is on the top, ln of x is on the top, gx is on the bottom, 3x is on the bottom. We're just labeling them to get ready for when we write out the quotient rule. So the quotient rule is the derivative of fx multiplied by gx minus fx multiplied by the derivative of gx all over gx squared. So we need the derivative of fx and the derivative of gx in order to finish this up. So the derivative of ln of x is 1 on x, as I showed before, and the derivative of gx, what's the derivative of 3x? It's just 3. So we'll fill in derivative of fx is 1 over x, multiplied by gx being 3x, minus fx, ln of x, multiplied by the derivative of gx, which is just 3, all over gx squared, 3x squared. So, if we were to simplify this, we could factor out, well, we could, first of all, we could cancel off the x, because 1 on x multiplied by x is just 1, because that'd be x on x. So it would just look like 3 minus ln x multiplied by 3. And if we were to expand the brackets 3x to the power of 2, if we were to expand that, we would end up with, or just bring the power in and square each one, we would end up with 9x squared. And we can simplify this further. If we factor out the 3, we end up with 3. 1 take ln of x over 9x squared. All I did was just bring the 3 out from the ln of x and bring it out from the, essentially if we were to expand this, we would get that. So if we multiplied by 3 by the 1, we would get 3. If we multiplied the 3 by the negative ln, we would get negative ln multiplied by 3. And so now that it's factored out, we can cancel it off because we have a 9 on the bottom. we cancel the 9 and we make it a 3, because if we have 3 divided by 9, we end up with 1 over 3. So essentially that's 1 times the invisible 1 that hangs around everything, just about everything. I'm getting carried away. So now this will look like 1 take ln of x over 3x squared. If you don't understand how I did that, practice more and more questions. If you're doing math classes or you've got textbooks, just practice. Practice makes close to perfect. Nothing's perfect, but you can always get close to it. But let's do another example, speaking of more and more. Example 2. You have hx, and we'll make that equal to x squared plus 3x all over ln of x. So here we have a function fx over another function gx, just like how we would if we were following the steps for the quotient rule. Funny that we're doing the quotient rule. So the fx will label as x squared plus 3x, and the gx we will label as the ln of x. Oh, I forgot to. We're going to need g dash of x, and we're going to need f dash of x, because the formula says we have to in order to solve it. F dash of x multiplied by gx minus fx multiplied by the derivative of gx all over gx squared. So, derivative of fx being x squared plus 3x, derivative would be 2x plus 3. You should know how to do this sort of stuff before you start focusing on other things like ln or e or trigonometric functions. That's why I'm not explaining in depth how I do this. Not that there's incredible much in this, but anyway. Gx being ln of x, so the derivative is 1 on x, just like before. So, if we fill this out, derivative of fx is 2x plus 3. Gx is just ln of x minus fx, x squared plus 3x multiplied by the derivative of gx, which is just 1 on x, all over gx squared, which is just ln of x squared. So there's not really much to simplify on this except this little bit over here, so that's what we'll do. Rewrite it out. 2x plus 3 ln of x minus, because we have x squared plus 3x multiplied by 1 over x, we can use this 1 over x and get rid of 1x from inside. So we'll get rid of the x squared and make it just a standard x, and we'll get rid of the 3x and make it just a 3. Just like this. And that will be all over ln x squared. Okay, so for another example on this exciting topic, h x, we'll make that equal to sine x, or better bring that down, sine x over ln of x. Again, function over function, sine x fx over another function, ln of gx. If we label them, fx we'll call sin x, and gx we will call ln of x. So, say so a lot, but you know, whatever. The derivative of hx is derivative of fx multiplied by gx minus fx multiplied by the derivative of gx all over gx squared. Derivative of fx, if fx is sin x, then the derivative is cosine. And if gx is ln of x, the derivative is 1 on x. So, if we fill this in, derivative of fx, cosine of x, multiplied by gx, ln of x, minus fx, sin x, multiplied by the derivative of gx, 1 on x, all over gx, which is ln of x, squared.